Everybody again. So today we'll be learning about similar solids. Three-dimensional shapes or solids can also be similar. Similar solids have the same shape, their corresponding angles are equal, and all corresponding linear measures, edges, diameters, radii, heights, and slant heights are in the same ratio. As with similar two-dimensional shapes, the ratio that compares the measurements on the two shapes is called the scale factor. Volume and surface area of similar solids. The following table shows the side length and volume of each of the cubes above. 2, 4, 10, and 2 times 2 times 2, which is 8, 4 times 4 times 4, which is 64, and 10 times 10 times 10, which is 1000. Here this is times 2, times 8, times 5, times 125. Notice that when the side length is multiplied by 2, the volume is multiplied by 2 cubed, which is 8. Here, the scale factor of lengths is 2, and the scale factor of volumes is 2 to the power of 3. Also, when the side length is multiplied by 5, the volume is multiplied by 5 cubed, or 125. This time the scale factor of lengths is 5, and the scale factor of volumes is 5 cubed. In fact, this pattern follows in a general case. Scale factor of volumes equals scale factor of lengths cubed. But considering the surface area of the cubes, you will also be able to see that the rule from page 237 is still true. Scale factors of areas equals scale factor of lengths cubed, which is this one. In summary, if two solids A and B are similar, the ratio of their volumes is equal to the cube of the ratio of corresponding linear measures, edges, diameter, radii, height, and slant height. In other words, volume A divided by volume B equals A over B cubed. The ratio of the surface area is equal to the square of the ratio of corresponding linear measures. In other words, the surface area A divided by surface area B equals A over B squared. The following worked examples show how these scale factors can be used. Worked example 12. The cones shown in the diagram are mathematically similar. If the smaller cone has a volume of 40 centimeters cubed, find the volume of the larger cone. So the scale factor of lengths is 12 over 3, which is 4. So the scale factor of volumes, which is 4 cubed, equals 64. So the volume of the larger cone equals 64 times 40, which is 2,560 centimeters cubed. Worked example 13. The two shapes shown in the diagram are mathematically similar. If the area of the larger shape is 260 centimeters squared and the area of the smaller shape is 24 centimeters squared, find the length x in the diagram. So the scale factor of area equals 216 over 24, which is 9. So the scale factor of length squared equals 9. And the scale factor of length equals the square root of 9, which is 3. So x equals 3 times 12, which is 36 centimeters. Worked example 14. A shipping crate has a volume of 2,000 centimeters cubed. If the dimensions of the crate are doubled, what will its new volume be? So the original volume over the new volume equals the original dimensions over the new dimensions cubed, which is 2,000 over new volume, which is equals 1/2 cubed. 2,000 over new volume equals 1/8, and the new volume is 2,000 times 8. The new volume is 16,000 centimeters cubed. Work example 15. The two cuboids A and B are similar. The larger has a surface area of 608 centimeters squared. What is the surface area of the smaller cuboid? What's the word cuboid? Yeah, no, but I mean, yeah, I know they mean cuboid. So surface area A over surface area B equals the width of A over the width of B squared, which is the surface area A over 608 equals 58 squared, which is 25 over 64. So the surface area of A equals 25 over 64 times 608. The surface area of A equals 237.5 centimeters squared. Cuboid A has a surface area of 237.5 centimeters squared. So that's the end of this video. Next video, I'll do the exercise 11.6. Bye-bye. And don't ask me what the letters at the end of the descriptions mean. I won't answer that until it ends, I guess. Bye.